Good evening, everyone, and welcome to the first astronomy public tour of 2014. So, this is going to be a bit of an experiment, and this has actually never been done before. Recently, we had a supernova. And because of that, we decided to hold a special occasion where instead of a single speaker, we bring out 5 speakers. And we will be having a panel discussion where you can ask questions about supernovae, what they mean for the universe, whether or not they'll destroy the Earth, or any questions that you might have about them. So here's how this is going to work. And before I talk about that, I should talk about our sponsors. This is an event in a series of events that is run by the graduate students of the Department of Astronomy and Astrophysics at the University of Toronto, and is produced in support, with the support of the Dunlap Institute for Astronomy and Astrophysics, the Department of Astronomy and Astrophysics, and the Canadian Institute for Theoretical Astrophysics, or CETA. So the way this will work is first we will have our special panel/lecture, and following that we will have the telescope observations and the planetarium shows. Now, as all of you probably saw when you came in, it is currently cloudy. So we're going to cross our fingers and hope that the clouds break and we might get a chance to see the supernova. But if it continues to be overcast like this, unfortunately, it won't happen. I'm very sorry. Winter in Toronto. So we will also have the planetarium shows, and those will occur in the usual McLennan building. And I will have instructions on how to get from here to there, and what to do once you get there after the panel discussion is over. So please stay seated after it's over. So as I was saying earlier, a supernova has occurred, a thermonuclear supernova in the galaxy M82. And this is one of the closest supernovae to have exploded and been observed by humans since the time of Kepler, essentially. And so it's a very exciting event, and we will be getting some incredible science out of it. And here to talk about this is our panel of 5 experts, and I will be introducing them, well, 4 experts, and I will be introducing them in order. So first up, we have Dr. Wolfgang Kersendorf. He did his PhD in Australia. And now he's here. Okay. And now he has come here and is currently a postdoctoral fellow in the Department of Astronomy and Astrophysics. He works on finding the lost companions to stars that explode as thermonuclear supernova. And we'll talk about that in his talk.
Works? I mean, no, that's often problems with technology. I hope everyone is warm. I mean, it's very cold outside, and I hope, you could take off your jackets. And before I start, I want you to sort of put your mind to a warm place, actually in spring, and I want you to think about May, early May, and it's a warm spring night, and you're sort of looking up at the sky, and you see a star that wasn't there before, and it's like very bright. It's unusually bright. And oh, what are you guys doing?
I see.
No, that's fine. That's part of the show. That's part of the mystique. And what you see here, according you see your other stars, and suddenly over the horizon, like a star appears slowly over the days, and you can see it getting brighter and brighter. And this is an immense event. I mean, this is really fascinating. And so this happened more than 1,000 years ago, and this is the first event I'm going to talk about. So one of the people that observed were located in Switzerland, in St. Gallen. And so these people were at a monastery, and they were very good at log keeping. So instead of blogs, what we have today, they actually wrote it down. And they had a log, and every year they had an entry. And I don't know if people can see this. It starts with an N, M, and then 111. Does anyone know what year that is? Very good. So the supernova went off there, and every year they wrote an entry, and every year they wrote only one entry. And in this year, and what year is that? In 1006, they wrote Nova Stella Apparuit. And that's as far as my Latin goes. They wrote much more about this, but they wrote that the supernova appeared, and they were very fascinated by it. So 1,000 years ago, they saw the supernova. But they were not only the monks. They were like, you could say they were very good at beer brewing and like, they had too much to drink. There were other people. There was a guy called Ibn Ruwayt. No, I'm sorry. Ibn Ruwayt, and he basically also discovered this, and he also wrote something about the supernova. He wrote, "I will now describe for you a spectacle that I saw at the beginning of my education." He was 18 years at that time. "This spectacle appeared in the zodiacal sign Scorpio in opposition to the sun, at which time the sun was in the 15th degree of Taurus, and the spectacle in the 15th degree of Scorpio. It was a large spectacle, round in shape, and its size 2.5 or 3 times the magnitude of Venus." So he compared it to another object. "Its light illuminated the horizon and twinkled very much. This apparition was also observed at the time by other scholars, just as I have recorded it." So he was not only observing it, but he was collaborating with other people, and he found other people see this as well. And not only in Europe and Asia and Middle East did this happen. Also is a picture of Ali. Also in China, in the Song Dynasty, people wrote about this. And the person that explained this wrote to the emperor and said, "This will bring 7 years of good luck," and he was promoted. I don't know if it had anything to do with it, but it might well be. So this was 1,000 years ago. 1,000 years ago, people were fascinated with the sky and recorded the sky. So now we're jumping ahead 500 years. These supernovae don't happen very often. So there was another one in 1181, another one in 1054, but then for a long time, nothing. And in 1006, a spectacle like this happened again. People saw a very bright star in the sky, and the person that this is attributed to is Tycho. And he saw the star, and first he didn't believe his eyes. I mean, like the Swiss monks, maybe he was drunk and he wasn't quite sure. And so he asked people on the sky and pointed up in the sky and said, "Look, also, do you guys see the star?" And I mean, he was just trying to prove that he's not crazy, but maybe people thought he was crazy because he was asking random people on the street if they see a star in the sky. But anyways, so he found another bright star and discussed it with scholars. At this time, what he found also that he could measure that the star didn't move. And the planets were the brightest things in the sky except the sun and the moon. And so he realized the star that was very bright did not move. And he presumed that it must be very, very far away. So he was one of the first person to figure out that the faraway stars are by no means immutable. They evolve like everything else, but on a much longer time scales. So we're again jumping ahead 350 years because I can't tell about all the stories that are. There's many interesting stories. So people hadn't really figured out what these things are. One thing that people slowly figured out, and this was Bart and Zwicky. These people. This is Zwicky. He has discovered many things about supernovae. They the first time introduced the term supernovae. Novae were stars like new stars. Nova were new stars that have been discovered. But supernovae, they didn't know there were different subclasses. And he figured out that these things are very, very bright. And he realized that they must be very, very far away. So he was the first one, or these guys were the first one that made a distinction between supernovae and novae. And he also said, these things had been discovered before. And he actually mentioned here in 1572, he mentioned Tycho's supernova. And he realized that this was not a nova, but a really large, really bright supernova. And they concluded that the phenomenon of a supernova represents the transition probably of an ordinary star into a body of considerable smaller mass. So subsequently, quite a few people observed these and looked at the composition. And what they found hydrogen and calcium and oxygen and iron, which was consistent with what stars are made of. Hydrogen, the main part. But they also discovered another part of object, and they called them different types. And they discovered that they didn't have hydrogen, which is the mystery, which is the main mystery we're going to be discussing today. And Laura and Martin especially will talk about this. So this sort of ends the discovery or the discussion about the supernova. But I think there's Type 1a supernovae are very interesting and have led to amazing discoveries, so I thought I'll extend a little bit further on this. So what happened at the time where Bart and Spieke was working, also Hubble, I'm sure you've heard of Hubble, made two very, very important discoveries. One of these discoveries was that the nebula which were presumed to be in the Milky Way were close nebula, that they were actually very, very far away. And how he did this, he used Cepheids, very bright stars, to measure distances. With these distances, he could measure the close galaxies and realize the universe was much, much bigger than we initially presumed. And he realized that these other galaxies were far away. But he didn't have the means to go very far, only sort of the local galaxies, as we call them now. The other discovery that he made, he looked at their spectra. And when things move towards us, they appear blue shifted. When they move away from us, they appear red shifted. And when they're, well, compared to when they're standing still. And so what he discovered, things that are further away move at faster velocities away from us. Everything is moving away from us. I think that's the main discovery. And so what he concluded, if he reversed the time, it must all be at one point in time, 13 billion years into the past. And so he discovered the Big Bang. But he could only measure this sort of Big Bang, he could only measure these movements from very close galaxies. And what happened, the supernovae, using supernovae as really bright candles, they can measure very far distances compared to the Cepheids that have been used so far. So for the next 50 years, supernovae and measuring distances was intertwined until 1998, where people tried to measure the deceleration of the universe. That means that the universe is slowing down because of gravity. And what happened is that they found the opposite, that it's actually accelerating. And this is another story, and another time we will talk about this more. This is a discovery of dark energy, and in 2011 people got the Nobel Prize for this, all using Type 1a supernovae. But not only did we discover a lot in the last 100 years, so the initial Type 1a supernovae of SN 1006 and SN 1572 that I talked about, but also Kepler supernovae, which is SN 1604, they were all recorded without the use of telescopes. And still people back then had the ingenuity to figure things out about them, and they gave us data which we can still use today. And with this, I'm going to end, and I'm going to hand over to Marten.
I thought Laura was going next. Okay. So next we have Professor Marten van Kerkwijk, who is a professor here at UofT. He works on both the origins and observations of Type 1a supernovae as well as neutron stars. So he's interested in compact objects of all sorts. He's also my supervisor. So, and we'll be talking tonight about the physics and root cause of Type 1a supernovae.
Okay, so I'll go on a little bit with telling you what we know about how supernovae work. And I thought I would title this that at some level I think the defining factor of a supernova is, strangely enough, that it's a star that's failing to be a star. That's why I called this the ultimate failure of being a star. And so to explain why I say that, I'll explain first what really I think is the essence of a star, so what it is failing. And I also want to, Wolfgang already alluded to the fact that observationally there are two types of supernovae, and it turns out there are also two types of failing to be a star. And those correspond to the two types he mentioned. So let me first sort of say, I'm sort of treating you a little bit here like my students, I'm afraid. So this is a slide from the lecture I sometimes give to an even larger number of people. And that is basically how I think about a star is sort of the 2-minute summary of a star. And that is really that its whole life is one long protracted battle against gravity. Because really, what is a star? It's a ball of gas. It's held together by gravity. And in order for it not to collapse, there must be very high pressure inside. And that's really the sort of key thing. There must be high pressure. Now, for a normal star, like the Sun, which is made of sort of normal gas, the only way to get such high pressure, enough to withstand the gravity exerted by itself, is to have really high temperature. So again, for a normal star, you must have high pressure, must have high temperature, and if you're very hot and space is very cold, that means you are going to lose energy. And that's what we see. So if people ask you, why does the sun shine? Many people say, oh, they're actually heard astronomy and they say nuclear fusion, and that is at some level true. But really, it's not, the essence is, it's not true. Even if nuclear fusion stopped right now, it would continue shining. It has no choice. It has high pressure inside, high temperature. It will lose energy. Now, of course, for the thing to be imbalanced, there has to be a source of energy that compensates for all this lovely warm radiation that we sometimes get to see in winter. And so you need an energy source. And there are really two sources. One is nuclear fusion. That's what the sun is running on now, hydrogen going into helium. And the other, if that runs out, then well, the star is losing energy. That means it gets less pressure and it will shrink, and that generates energy. It's a bit like how things falling further to the ground that generates some extra energy. So either you shrink or you have nuclear fusion. But in the end, all your fuel is going to run out, and you're going to keep on contracting until maybe ultimately something else than thermal pressure can balance gravity, and we'll soon need that. But the essence of the star, which is what a supernova fails to do, is really that first one, that you have to support your own weight. And so how does that fail? There are two ways of failing this. So basically, in what we call core collapse supernovae, you can have a catastrophic loss of pressure, that your pressure suddenly drops away and therefore the thing starts to collapse. And it's actually only the core that collapses, so the term is appropriate. And this happens in stars which are much more massive than the sun. So they run through their hydrogen, burns all to helium, the helium fuses to carbon, the carbon to oxygen, the oxygen to neon, neon to silicon. I think actually swapped through around here, but oh well. In the end it keeps on fusing, it gets hotter. Every time the fuel runs out, it contracts, gets hotter still, and then you get all the way up to iron, and you make a nice iron core of a little over a solar mass. And then when that starts growing, it also would really love to continue fusing. It's contracting because it's losing heat. It's getting hotter and hotter, but iron is the perfect element. It cannot be fused into something else and yet generate more energy. So if you fuse hydrogen to helium, you gain energy. If you try to stick iron nuclei together, it doesn't work. It costs energy to do that. And at some point, the temperature becomes so high that the iron actually gets broken apart again. Well, that is not good news. That means that you're using energy to break the iron apart. That means you're losing pressure. You start to shrink. You heat up even more. You break more iron nuclei apart, and you collapse. And then the collapse to a neutron star, which is this, as Charles mentioned, the other type of object I really love to study, in the end sends by a mechanism that is not very well understood, to say the least, sends the rest of the star out into space. It leaves a neutron star, but the rest gets sent off into space. And actually even if it's cloudy, near the telescope, Evan O'Connor will be sitting with showing his simulations of that process. This, however, is not the type of supernova we are talking about tonight. We're talking about another type of supernova which sort of does the opposite. It's called a thermonuclear supernova. The term was used already, and instead of a catastrophic loss of pressure, we have a catastrophic gain of pressure. This is more like a bomb. So what happens here is that you have a dead object already, a white dwarf. It's made mostly of carbon and oxygen. The fuel, the hydrogen, has been burned to helium. The helium has been burned to carbon and oxygen. No hydrogen is left. And you see the link here with what Wolfgang was saying. And somehow, and this is really the puzzle that we'll discuss further, in this dead object, you light the nuclear fire again, and it happens in a way that is completely unstable. It's a runaway, it is like a bomb. It is a runaway fusion. You turn all this carbon and oxygen into nickel, which then later decays into iron. And in fact, much of the iron that we have around here is made in these type of explosions, while much of the oxygen and carbon is made in the other type of explosions. And this happens at really, really high density. White dwarfs are very dense already. To make nickel, you need a white dwarf which in its interior has a density of more than 10 tons per cubic centimeter. It's nothing compared to a neutron star, but it is dense by other standards, right? Water is 1 gram per cubic centimeter, so this is 10 million times denser than that. Or it might be, depending on what exactly you think you happened, it might even be 100 times more dense. And these supernovae are powered by nuclear energy. Now I want to tell a tiny bit about these white dwarfs. So really and that's one of the things I'm intrigued with, is what happens if you squeeze matter a lot. And it turns out that elementary particles, in particular electrons, don't want to be in the same position. That it was found out in the turn of the century, same good times that sort of Zwicky and so on lived a little bit earlier. And as you squeeze them, these electrons, they start to resist that squeezing. And one way of seeing how much they resist that is to use something that you probably heard about, and that's the Heisenberg's uncertainty principle. So in principle, you can do this calculation at home. It's actually not so hard. It's a simple equation, but anyway, I'll walk you through it. So you may have heard that you can, for elementary particles, you cannot measure the position and the velocity at the same time. And you may have thought that this has something to do with the measurement, that somehow it's impossible to measure the position and the velocity at the same time. But it's much more basic than that. The electron itself, if it is confined to a very small space, it does not know its velocity. It does not know its velocity in a typical white dwarf to 100,000 kilometers per second. So some white dwarfs will be, it doesn't really know. But some really are going with 100,000 kilometers per second, which is a third of the speed of light in a sort of typical white dwarf. And that is what provides the pressure in this white dwarf. Now one of the ways, and that's also what makes this unstable. So if I ignite fusion in this, that means that I start heating up this white dwarf, then at first these electrons are already going at 100,000 kilometers per second. So that I make it hotter doesn't change anything for them. But it does get hotter. That means the fusion goes faster. And it does get hotter still. Fusion goes faster, it does get hotter. It's a runaway until finally they start noticing, hey, it's so hot now, I'm really moving at 150,000 kilometers per second. And then the whole thing blows apart. Now, the question though is, this is all nice. We have these white dwarfs. How do we explode it? Well, we actually don't know. In one way, because really this is stable. It's fine. These electrons are moving very fast. This is a white dwarf. Our sun will end up like that and it will remain a white dwarf forever. There's really no doubt about it. But what if you could change it? And now imagine that you had a white dwarf. There is a nice, I'll actually show you a figure from a scientific paper from the 1960s. This is how the radius of a white dwarf changes as a function of mass for different compositions. It doesn't really matter that much what the different curves are, but as you go up in mass, you see that the radius becomes smaller. So as you make a white dwarf more massive, it has more gravity, the electrons need to be squeezed closer together so that they move even faster and have higher pressure. But you also see that all the curves either have some hook, which I won't discuss, or they go to zero at some mass. And what happens there is that as you move you compress these white dwarfs more, the velocity goes up, and at some point you reach the speed of light and they can't go any faster anymore. So they can't give much more pressure anymore as you squeeze stuff further together. And the thing can't be any more massive. And that's one of the ideas for how how you ignite carbon fusion, is that you just keep on making the white dwarf more and more massive by throwing stuff on it, say from a companion star. So the sun will never do this, it has no companion star. But if you keep on throwing more mass on it and you squeeze this white dwarf, at some point you might get so dense that you just squeeze the carbon nuclei inside each other, they start fusing, blow up. So that's one way of exploding it, and that's the standard picture that people have. But we're actually not really sure if that's the right picture. So another way is maybe that's, well, normally if you want to light a bomb, maybe you put a blast cap in it. So that's also possible. You could think, hey, I'm throwing stuff on this white dwarf, maybe that stuff, that's hydrogen, that could explode. Well, that doesn't actually do anything. We see that as the regular novae, not very interesting. But if you throw helium on it, it's possible that that gives a strong enough explosion that you could ignite the core. So you can blast it, maybe. And my favorite model, which not that many other people believe, but well, I do, and poor Charles has to work on it, is that you actually take two white dwarfs, you merge them together, and I think, and he hopefully will prove, that but don't worry, he'll get a PhD also if he proves me wrong. I'm a good enough scientist for that. Is that in this merger you manage to make things dense and hot enough just basically by friction. So if you think of this, there are the three ways of, if you think of a jar of nitroglycerin, you could sort of either squeeze it and it will explode, you could hit it and it will explode, or you could rub two sticks together and hope that you'll get it hot enough, and that's sort of what I'm hoping to do with merging two white dwarfs, which is a bit more violent than that. And so basically there's a question of how do we ignite it, and then in what kind of system does this happen? Is it really that there's a slow trickle of matter going to the other star, or is it two white dwarfs merging? And that part Laura will now talk about. And then I'll come back.
So next we have Professor Laura Chumwick from Michigan State University. And Laura actually was scheduled to give a colloquium or specialist talk several months in advance, and just out of serendipity, the supernova exploded. We asked if she'd be willing to give a public talk, and she said yes. So thank you so much for attending. Laura works on radio observations of Type 1a supernovae and their environment, and she'll be telling us why observing these things, especially this most recent supernova, can provide incredible and useful science. Thank you.
All right, so just to reiterate what Martin just said, right? The problem we're all trying to figure out right now for 1As is that we know that it's a white dwarf that explodes, but white dwarfs are stable. So the question is, how do you make them explode? This is the question everybody wants to know the answer to. And one of the best ways to answer this question is to sit around and wait for a 1A to go off very nearby to us. And luckily for us, 2 weeks ago, the most nearby supernova 1A went off in the past 30 years. So this is 2014 J. This is the supernova that is right up above our heads right now, but unfortunately through the clouds. It went off in the nearby galaxy called M82, or otherwise also known as the Cigar Galaxy. And it is at 12 million light years away. I converted that right, yeah. 12 million light years away. It's worth noting that those supernova that Wolfgang talked about, the one that went off in 1006 and the one that went off in 1572, those actually went off in our own galaxy. And that happens fairly rarely. So actually the most recent supernova that went off in our own galaxy has a very unglamorous name of G1.9 plus 0.3. It went off 100 years ago. So people could have seen it. It could have been whopping bright, like the one that was seen by the ancients and by Tycho. But actually that supernova went off in the center of our galaxy, and it went off behind an enormous amount of dust. And so even though it went off only 100 years ago and people were looking at the sky all the time, people saw nothing from it. We actually only discovered it 5 years ago, and we discovered it in X-ray and radio wavelengths, which are wavelengths of light that can actually see through dust. So this just goes to show you the universe can be tricky, right? This supernova is way, way further away than that one that went off 100 years ago in our own galaxy, and yet it's much brighter because it's not extincted by dust. So it's just a fun fact. And actually our own galaxy should have about one supernova every 100 years, so we should be about due for one in our own galaxy any day now, although again, it could go off behind a huge amount of dust and we might just miss it. Okay, anyway, this is a little history. The one that went off, so before our new friend 2014 J went off, this was the closest supernova of type 1A that went off. It was in 1986. It had the name of 1986 G, and it went off in this galaxy at roughly the same distance as M82. So you can see that supernovae that go off this close by really are fairly rare. We're talking like once every few decades. So we're very excited about 14J. And right, the reason that we're excited about a supernova being so close is that when something is closer, it's brighter, and you can study it in much more detail. You can study it across the entire electromagnetic spectrum, and you can really just get beautiful signal on it, right? You're not limited by the fact that things are faint, and you're not limited by the fact that things are very noisy. So astronomers are really going to town on this. People all over the world are observing 14J at all sorts of different wavelengths. Amateurs are observing it. Professionals are observing it. One cool thing about 2014J is not just that it was nearby, but it was also that it was discovered very, very early. This is its light curve. So right, the light curve is how the brightness of the supernova varies with time after outburst. And those are all different colors that we've observed it in. So we've been observing it in great detail from the ultraviolet to the infrared. But you can see that we have observations of it basically from the very first time, right when it exploded. We have some non-detections at very early times, and we just watched it grow from basically anonymity to become a supernova. So we've known about this thing basically from the very moment it became a supernova, and that's really exciting because we can test some of our theories the best at very early times right after the supernova. Okay, but right, so getting back to what some of the physics that Martin was talking about, the ultimate question that we want to know is how on earth do you destabilize these white dwarfs? And the general answer is that we think that the white dwarf has to have some kind of companion star, right? It has to be in a binary system, it has to be orbiting, it has to have some other star that's orbiting around it. And the companion star could look like a red giant, right? So a red giant is a big, puffy star. It's, so if the sun became a red giant, its size would almost envelop the Earth's orbit. Be really, really big, right? So the white dwarf could have a red giant companion, and in which case red giants are really bright, they're really big, they'd be relatively easy to detect. The white dwarf could have a companion star that looks a lot like our sun, so just a normal adult star. We call those main sequence stars. Or the white dwarf could have a companion that is another white dwarf. And so astronomers really want to know what on earth is the white dwarf's friend in these type 1a supernovae, and how is that friend destabilizing the white dwarf? Okay, so one of the simplest things you could do to try and look for the friend of the white dwarf is you could, so in a nearby supernova, like 2014J, people actually look at that galaxy a lot. And there are some really beautiful Hubble images of the site of 2014J before 2014J went off. So that on the right, you have a Hubble Space Telescope image of the location where 2014J went off. And on the left, you have a really nice image of 2014J after it went off. And that really nice image on the left lets you figure out what lets you pinpoint the center of 2014J really, really closely. And then you can go back in the Hubble image that was from before the thing exploded and say, is there anything there? Is there any evidence for a companion star? Right? So the white dwarf itself, the white dwarf that exploded, is going to be very, very faint. But if it had, say, a bright red giant companion, you should be able to see it in the pre-explosion imaging. And so there should be something, if there was a bright companion star to the white dwarf, there should be something sitting in the middle of that red circle. And there's not. And so this is fairly good evidence that white dwarfs don't have red giant companions. Whatever their friend is, we think they have to have a friend, but whatever their friend is, it is pretty faint. And this is just another example of a supernova that went off in our local universe where we did exactly the same thing, and again, there's nothing at the position of the supernova. So this is one of the clearest pieces of evidence that the friends of white dwarfs that explode as type 1a supernovae are not red giants. But so we still have these two other possibilities that might explain the majority of type 1a supernovae. One would be that the friend is a sun-like star that still has a lot of hydrogen in it, or the friend could be another white dwarf. In which case, if it was another white dwarf, it would be pretty inconspicuous and pretty hard to see. All right, so one of the easiest ways to tell the difference between these two things is to study the environments of supernovae of type 1a. So the thought was that if a supernova of type 1a has a sun-like star, it's that when the white dwarf eats material from the sun-like star, which is going to have to happen if the sun-like star is going to disrupt the white dwarf, some of that stuff that the white dwarf has been eating will get thrown back into the environment. And the white dwarf will have bad table manners. So it'll look something like this, right? So it won't be food, but it will be gas strewn all around the environment of the supernova. And you should be able to see that gas. You should be able to actually observe it. And so if the white dwarf has a sun-like star, you can imagine it like this guy from Monty Python, right? But if the white dwarf has another white dwarf as its friend, you can imagine like this very cultured woman who has very good table manners. So I spent a lot of time doing observations of white dwarfs of type 1a supernovae to figure out what kind of table manners the white dwarf had. And basically what you can imagine you're doing is, so when the supernova goes off, it emits this giant blast of energy, and as that giant blast of energy sweeps into the environment, it will interact with whatever is there in the environment. And that interaction will give you light at a bunch of different wavelengths. It will give you light at radio wavelengths. So this is a picture of the VLA. This is my favorite telescope. It'll give you light at X-ray wavelengths, and it'll even give you light at optical wavelengths. And so we can look at supernovae at all these different wavelengths and see if we can see what kind of table manners the white dwarf has. And so I've done this now for 14J, and we have also done it for the supernova that went off very close by just a few years before 2014J. It was called 2011 FE, and it was also a really big deal. It went off maybe twice as far away as 14J. And in both cases, what we find is that there's no radio emission, which basically means that white dwarfs have very good table manners. Basically means that the environments of type 1a supernovae are very, very clean, very, very low density. There's no evidence of there being gas spewed out while the white dwarf is eating. Also, there's no evidence for X-ray emission in either one. So this is just another independent confirmation that white dwarfs have very good table manners. And finally, so Wolfgang was talking about how type 1a supernovae don't have clear signs of hydrogen. But you can do really late time observations at optical wavelengths to see if maybe there's even the teeniest, tiniest bit of hydrogen in their spectra. And the answer is no. There's no hydrogen that we see in either in 2014J or its other nearby cousin. So basically all of this together, all of this multi-wavelength evidence is consistent with white dwarfs indeed having very good table manners, right? They don't look like this guy from Monty Python. They basically look like they have, whatever they have eaten from their friend, they have eaten it very neatly. And so this is much more consistent with them probably being the merger of two white dwarfs than having eaten from a sun-like star, which would be good for Charles's thesis, I guess. So yeah, okay, so that's basically, so I mean, this just gives you some sense of where the field is right now, what sorts of tests we're trying to do to figure out what type 1a supernovae really and truly are. And so I'd say all the evidence right now for 2014J and its other nearby cousin is that this is the most consistent model. But it's not proof still, we're still working on it. So yes, okay, that's all I have to say I think now. And Martin has a little bit more to say. A little bit more. Is that okay, Charles?
In fairness, it's good. We'll do it. Okay, so this is probably the part that Charles really wanted to go on to the panel, and he's right, because now it sounds like his thesis is all safe. But I think I also want to be honest. So I've sort of summarized what Laura just said. That you have these predictions. We call this in technical terms the single degenerate channel, because there's one degenerate object, the white dwarf. It had all these predictions that there's mass, basically. There's a companion that should still be seen. Wolfgang didn't mention, but he has really looked for former companions. This thing explodes. There should be something left. There's nothing. There should be hydrogen stripped off. And Laura said there's no mass around, and there isn't, mostly. But there is some, but it's usually a bit further away than what she can directly see. And we're actually together collaborating on trying to understand this. So I thought, this is a little bit silly perhaps, but rather than keep this beautiful story that we almost solved this, I would tell you again why we actually haven't. So this is the one supernova remnant that's also historical that Wolfgang did not discuss. And he showed two pictures. It sort of had nice colors like this, but they looked really regular and round. This is the one discovered by Kepler, and it does not look regular and round. And there was very recently a type 1a supernova quite far away, where people even said, we found it, we found the mess around this stuff. And now we know that they actually have giant progenitors. Now they were actually wrong, I should say. But there is still a lot of debate. And the only thing I wanted to say is actually that I think in the end there's actually a lot of mess around it. It's not a little bit. There is among some. Most of them are very, very clean, but some have like a solar mass of junk around them. And that actually this makes sense for the double white dwarf merger. And now I'm really sorry for Charles, but I'll go through this. How did these things form? So how do you make a white dwarf? So there's two scenarios here. Two stars. On the left you have one, and on the right you have two. You have two stars on both sides. So the more massive stars goes first, becomes a giant, becomes a white dwarf. That's the little blue dot. But as it becomes a giant and starts to interact with its little star, they enter each other's envelope and they come much closer to each other. So this is above Wolfgang's head here. So you have a small red star, that's a sun-like star with a white dwarf. And then later it starts to do this little yellow dash, is this accretion disk. It starts to donate matter to the white dwarf, and that thing can explode. So that's one scenario, and that's what we discussed. The other scenario is that you become a giant, you become a white dwarf, but you don't engulf the other star. But when the other star in turn becomes a giant and tries to make a second white dwarf, it does engulf the white dwarf, they come much closer together, and you have two white dwarfs, and then the idea is you wait a long time, you merge these two white dwarfs, and you make a supernova. And that's why we say normally we think this is clean, because you have these two white dwarfs here, they take a long time to get together, and by then all the mess is gone. But what if you actually exploded very closely after what we call a common envelope phase, because hey, they're going in the same envelope, you would still have this envelope around. And how would that look like? And actually, so that's something Laura and I are actually trying to explore. And we think it might look a bit not like this thing, which is called a planetary nebula, the biggest misnomer ever in astronomy. This is if you have a giant star and it sends out its outer layers and you leave a white dwarf, it looks like this. This is what happens if you have a single star. But if you have another star going inside its envelope, it sometimes doesn't look all that round anymore. And so these ones say here in the bottom, which are very asymmetric, there are often binaries inside there. And so we think that if one white dwarf entered the envelope of another, another giant star, it might look something like this. Or something like this, or this, or this. They're all like binaries, or something really beautiful like this one. And then if it explodes, it would initially, if it goes off in the eye of the cat's eye nebula, I don't know actually if that, I think there's a binary in there too, but it's not two white dwarfs, but oh well. If it were to explode in there, at first you might not see anything because you're in the hollow in the middle. But then after a while, when you start, your ejecta start expanding, you might see something like what we have seen for another really nearby supernova. That was the last close core collapse supernova, 1987A. And now that was a core collapse, so it's a different reason why they exploded, but it exploded in a similar kind of environment, and we're almost certain that that also was two stars which merged with each other through of an envelope, and 1,000 years later or so, the supernova went off, and now its ejecta are hitting that envelope. But this supernova went off in 1987, and now we are really seeing such a beautiful ring. So some, 26 years later, and so that's partially what Laura and I are hoping to do with some old Type 1a, say this 1983G, look at it back and see maybe it wasn't emitting radio then, but maybe it's now, because now it's running into some stuff. So that really is the end. We did promise, Charles, that we would not stick to time.
Yes, they did. So next we have a mini talk by Kelly Lipo. Kelly Lipo is also Martin's grad student, and she works, she works on surveys to try to find what Martin earlier said were single degenerate objects. So things, a white dwarf and a non-white dwarf companion that could one day create a Type 1a supernova.
So many microphones. Okay, so I am going to try to be quick here. So hi, my name is Kelly Lipo. You may remember me from the December public tour, and if you're interested, I'm also giving the March public tour. So fun, but anyways, this is what I do my research on, and what I look for is normal stars, so stars like our sun, with a white dwarf companion. And the idea goes something like, if you know how many babies are born in Toronto, you can sort of figure out how many pregnant women that you need, or say storks, right? So if you go out and you count the number of pregnant women in Toronto and you say, well, gosh, there aren't enough to equal the baby rate, well, maybe some babies come from storks, right? So this is what I'm doing. I'm going and I'm trying to count the number of normal stars with white dwarf companions. And where I'm doing that is in this galaxy called the Small Magellanic Cloud. So here we have the Milky Way galaxy at night. And right over here, this little fuzzy blob is called the Small Magellanic Cloud, and it's a little galaxy that orbits the Milky Way galaxy. And what's cool is that it's close enough that you can actually count individual stars in it, but it's far enough away that you can see the entire galaxy in one go. And we can't see the entire Milky Way galaxy because we happen to be in the middle of it. And so what I've done is I've gone in this galaxy and I've looked for a couple types of white dwarf with some other star pairs. And what I found is that there aren't nearly enough of them to match the rate of supernovas that we see. So this is another piece of evidence that says, well, maybe most type 1a supernovae don't come from this normal star in a white dwarf scenario, but are more likely to come from two white dwarfs. And that is all.
Get them on there, I guess. And lastly, we have a micro talk from myself. Okay, I am going to attempt to keep this under 40 seconds to see if I can. The answer is probably no, I can't, because I can't get all this thing working by then, but we'll see. So, as Martin alluded to earlier, I am his graduate student, and I work on whether or not two white dwarfs merging together can rub against each other hard enough that they eventually heat up, and then after they finish merging, they explode. There we go. Magic of television. Nope. Yes? No? Okay, that's wrong. Current slide. Okay. So the awful thing about white dwarfs is that they're not very bright. They're not very bright objects. They're hot, but they're the corpses of stars. They're very dim. You can't see them as far away as you can see red giants or supergiants. So if we're going to find the cause of type 1a supernovae, and all we have are these type 1a supernovae happening in other galaxies, and they come from two white dwarfs that come together and explode, then we would never see them before they explode. So how do we prove that this is actually the cause of type 1a supernovae? Well, we run computer simulations that hopefully can tell us what the end result will look like. Does the source of type 1a supernovae change the nature of the explosion that happens afterwards? So to figure that out, it started without me. Okay. Technology from the beginning. Okay, so here we have two white dwarfs. The one on the right, I believe, is very slightly heavier, and therefore it does less work than the less massive one, because the less massive one gets ripped apart more easily. Now, the colors indicate temperature, and red indicates a temperature of about 100 million degrees. So this isn't just rubbing two hands together and lighting a fire. This is 100 million degrees. So the question is, can this object, after the two white dwarfs come together and form the single super hot object, can this thing eventually explode? The answer will be printed in my thesis. Thank you. So, we now finally come to the Q&A session. So we have a microphone there and a microphone there, because this room is huge and it may be hard to hear from the back. So for those people with questions, could you please line up at either microphone and I will point you out.
So the first question is over here. And although we're looking for a companion object, could there just be a gravity field there that it's not getting enough light or energy tugging on the dwarf's gravity field?
There actually have been really weird speculations about how you, since it's so hard to find out how to do it, maybe you do it with something crazier. We try to, I sort of would go with
So if there's two kinds of supernovae, why are they called 1A and 3?
They're called 1A and 2. So there's type 1. So I lied a little bit. So type 1 doesn't have hydrogen. So that's how they were classified. They found things with no hydrogen, and they found things with hydrogen. And things with hydrogen were... It's okay. I'm pretty loud, I guess. Things with hydrogen were pretty easily explained because most stars they figured out had hydrogen, and I mean Martin explained very well how a star works, and so they said, well, you know, these they named them type 2, but before then they found type 1. And type 1A showed silicon, and now we know that this is what we were talking about all along, the thermonuclear explosion of a dead star called a white dwarf. But there's two other type 1s, type 1b and type 1c. And so type 1b and type 1c are basically big stars which have lost all their hydrogen and only have helium and carbon oxygen left. So these are the multiple types. So there's type 1. There were many more types, but they got rid of them because they could group them into the, I don't know, 4 types that we have now. Does that answer it, maybe?
Yeah, I think so.
Okay, nice. Thank you.
I have a question for Charles' scenario of 2 white dwarfs colliding into each other. Because that, would that still be a type 1A supernova because the mass would be more than 1.4 stellar masses? And then would that also be more than 1 standard candle?
It's an excellent question. I'll start by clarifying that this is not my model. This is my supervisor's model. He invented it in 2010, and there's a paper out to prove it. So that's an excellent question. So, okay. This works? Okay. Okay. So, one of the weird things about type 1A supernovae is that to first approximation, they have very similar brightnesses no matter where they go off in the universe, which is why we can use them as standard candles, and this is how people use that to discover dark energy, that the universe is accelerating. So for a long time, people had assumed that to get this, you would need a bomb basically the same strength. And to get that, you need a white dwarf exploding that had pretty much the same mass. And a natural mass to do that, because it also represents the point at which the white dwarf collapses, is something called the Chandrasekhar mass. It's a little bit more than 1 solar mass. And past that, white dwarfs become unstable because basically gravity becomes too powerful. You have electrons that end up going near at the speed of light, and your white dwarf can't hold itself together.
Yeah. Are you going to say something more?
Go ahead.
Sorry. Doing this in front of 250 people, but I always feel that should be completely honest. And so these things are not, I mean, Charles sort of said, oh, they're somewhat standard candles, but they're actually not. I mean, there are standardizable candles, which is a big difference. So they actually have somewhat slightly different brightnesses, and the fainter ones last shorter, so they really send out about a factor 10 less energy than the brighter ones. So the idea that it is really a standard candle is it's not quite right. They're standardizable, and so that actually goes against this whole idea that it's one fixed mass, which people did think for a long time because it's such a nice picture. But if they had thought clearer, they wouldn't have thought it, and it's really good for 2 white dwarfs because, as you said, they don't have the same.
So yeah, with the 2 white dwarfs merging like that, the 2 white dwarfs can have masses that don't add up exactly to the same mass everywhere in the universe. And because you have this range of masses, you can have a range of bomb strengths, and you can have a range of explosions. And we actually see that in nature. The first part of your question was, is it still a double degenerate system? Is it still a type 1A supernova? So the definition of a type 1A supernova, as Wolfgang alluded to earlier, is that you don't see hydrogen, you don't see helium, and you see strong silicon lines. And if you explode something that comes out of one of these mergers, you would still get that.
Just a quick question. How long will it be visible to an amateur?
Probably 2 months.
3 months?
Yeah. So just recently reached its maximum brightness a couple days ago.
So we can wait till it gets warmer outside to go and see the sun.
It's going to be pretty faint by 2 months from now.
So to ask another question, what do you mean by visible? So I guess, I mean, it depends on what telescope. I mean, it depends on how big your telescope is. We tried here in Toronto, actually, with Mike Williams, who will later show you the night sky, to see it through the 16-inch telescope at peak brightness, and we could not see it. This is because the telescope is not big enough, but also because the site that we have here is not optimal, so we have a lot of light pollution. So please, people, switch off your lights so we can see the supernova. But I mean, you know, in theory, it would last a few months.
But it's going to decline quickly in brightness?
Yeah.
Unfortunately, Earth hour already comes too late. So. On the right.
Hi there. My question is about supernovas that turn into black holes. And also a question about, there's a massive black hole in the middle of the galaxies. It's speculated like that. So what causes that formation of the massive black holes?
Okay, so the type 1A supernova, the white dwarf supernova we've been talking about, won't ever form a black hole. Basically, it kind of goes through, burns through the whole white dwarf and doesn't really leave anything. But that other type of supernova, the type 2 supernova, if you have a really, really massive star, there's some thought that that's the type of thing that will form a black hole. So it could form a neutron star, but if it's even bigger than that, gravity wins and the neutron star doesn't, and you form a black hole. So that's how you form, you know, sort of a black hole with around the mass of the sun, that sort of thing. So there is the thought that there is a black hole at the center of the Milky Way galaxy, and you can actually watch stars go around it, and you can calculate from their orbit that there has to be this really massive thing there that's not giving off any light, black hole. And so there is a question about how you get something that massive, right? And so there's a thought that, well, you start off maybe with a solar mass black hole and it just keeps eating stuff and keeps getting more mass, but the details of how that happens are actually a little unclear.
On the left.
You mentioned fusion stops at iron, so I'm just wondering how you get heavier elements past iron.
Yeah, so actually, a very good question. So in a type 1A supernova, you basically don't, because the fusion, it stops there and it's happy there. In a core collapse supernova, you basically need something special, and there's some puzzles here. You basically, in a core collapse supernova, when you form the neutron star, you also, the outer layers get thrown out, as I mentioned, and as that happens, they get really hot. And there's the process by which fusion happens is they're not in equilibrium anymore. You have a lot of free neutrons flying around, and they stick to the material. So that's one way in which you can make some of them. You can actually make that in some, strangely, also in solar type stars very, very late, but that's not so much. And the other way to do it is actually take neutron stars, which are made purely of, you can think of them almost as one incredibly heavy element. There's 1.4 solar masses worth of one element. Take two of them, just like the two white dwarfs, merge them together. They will almost certainly form a black hole, but they will probably also throw out some. And if you think then there flies a clump of neutrons, and what will it do as it flies out? It doesn't have to be neutrons anymore. The neutron starts decaying, and they might make the heaviest elements that we know. Many people think that they're actually made from two mergers of two neutrons. So it's a very good question. Yeah.
So the neutrons are just the neutron decays into electrons.
Yeah, so normally, right, if you have a free neutron, it becomes a proton and an electron. But if you have a clump of neutrons, they would, and the neutrons start decaying, they would form really heavy nuclei. Just the moment they sort of say, oh, actually I'm stable, let me not then the other neutrons don't decay anymore until uranium a lot later. Yeah.
So are there any other questions from the audience? Other people sitting down who still want to ask questions. Well, if not, we have two more questions, and all the panelists will be here after the question period is over. So, on the right.
I've heard of a type of magnetic star. I think it's called the magnite, which are produced by supernovae. Do you have any information on that?
Okay, that's me. I study those things. So, yeah. So in these neutron stars that you make in the core collapse, they often have a magnetic field too, like the Earth has. And we see some of those. Their magnetic fields are not. They're not incredibly strong. Only 1 trillion times stronger than that of the Earth. So that's weak by neutron star standards. And then we see those as they emit radio pulses. We see those as radio pulses. And some, for a mechanism which we don't completely understand actually why, some are even 1,000 times stronger than that. And their fields are so strong that they can, the neutron stars are crushed, they can deform them and crack them, and they can make enormous flashes. And they're called magnetars. I think that's what you were thinking of. Yeah, they're called magnetars because that is sort of, the things that we see from them are all because they have such an enormously strong magnetic field. It dominates everything. Okay.
Last question.
I was wondering, have any of the surveys revealed any nearby candidates? Like, for example, for core collapse supernova, I believe there's some stars like Betelgeuse, which are fairly near us and are candidates for those types of supernovas. At some time in the future, are there any known nearby candidates for 1A supernovas that might happen, in the near future?
So yes, although it's very uncertain, but one of them, one of the most popular scenarios is when a white dwarf has a giant companion, and it shows these novae outbursts. It has nova. And maybe once every decade. And one of those just exploded last night. So actually, we have a nova from a supernova 1A progenitor that's just going off right now. People are going to be having a whole frenzy studying it. But yeah.
Yeah, and beyond that, there are a couple other sort of the very best white dwarf with a normal star companion. There are something like maybe 6 of those in the Milky Way. So yeah, there are a couple in our own galaxy that we know of, but when they will explode is probably not in our lifetimes, unfortunately. And
as we said, we see these systems, they look right, but we don't really know whether they will explode as type 1A supernovae. That was the standard picture, but as Laura said, for the ones that we actually see, we don't see those giants. So how does this work? We don't know. But there are definitely, for all the ABCs that she had for the different possibilities, we have systems which look just right. It could go off any moment. This is, of course, any astronomical moment, so it could be 100,000 years. Very soon.
Well, thank you for everyone who came up to ask a question. And let's thank our panelists once again.